So we were discussing Dirac operators. We mostly spent time while muted going off on a tangent about Dirac operators on odd-dimensional manifolds. They all have index 0. So to make an interesting problem, you have to do something else, which I'm not going to talk about. And let's get back to these guys here on even-dimensional manifolds. And in order to construct the Dirac operator, the major part of the trouble is to figure out what the thing should act on. That's one of these spinor bundles. As I discussed last time, when you build this operator, if you situate this operator within the context of Hilbert space theory, think of it as a so-called unbounded operator, it becomes a symmetric operator, and that symmetry makes its index 0. So that's not the thing whose index you want to calculate. It's this thing whose index you want to calculate. It's part of the whole package of ideas of Clifford matrices and spinor bundles and so on, that the bundle STM actually breaks up into two pieces, a positive piece, direct sum, and negative piece. And what the Dirac operator does is it exchanges them in the sense that the Dirac operator applied to a plus section is always a minus section, and vice versa. And so this thing is a Fredholm operator in the sense that its kernel and co-kernel are finite dimensional. And this is the index that we want to calculate. And more than one way to do this, but we're going to do this using K-theory. As I mentioned, there are potentially lots of Dirac operators out there. First of all, on a manifold M, there may be no Dirac operator. But if there is, there may be lots of genuinely inequivalent ones. So you have to specify which Dirac operator you're talking about. And the way you do that is you specify this particular choice of spinor bundle, this particular choice of bundle of a certain particular dimension, 2 to the k, if M has dimension 2k. And this bundle has to have be equipped with a particular choice of so-called Clifford multiplication, as we discussed last time and is discussed in the notes. Okay, so you have to specify all of that before you can say what is the index. You have to ask what is the operator first. That means choosing or somehow identifying one of these STMs, and then you can proceed. Okay. And in order to describe the answer, we need to say a little bit about K-theory. So this was invented by, of course, Satir and Hissebrook. So they invented an abelian for each locally compact reasonable space, Hausdorff space. They invented K of X, a certain abelian group.
Sir, I had something to ask.
Yeah, question?
So, STM is the tangent bundle, or?
EM is the tangent bundle.
Right.
S of TM is something that you associate to the tangent bundle. It's a complex Hermitian Z2 graded bundle equipped with one of these Clifford multiplications of the tangent bundle. So it's possible to think of each tangent vector over a point of M as being an operator on the corresponding fiber of STM over that point.
Thank you.
So that's that extra structure that S of TM has. Anyway, back to K-theory. This is, of course, what, as I've said more than once, what Kasparov reinvented. He thought about how to define this better, and we've discussed what the definition is. And last time, we discussed a quite general and maybe a little bit complicated notion of cycle. for this group. So according to Kasparov, if you have families of, I'm not going to write down the whole definition that we discussed last time, but you're supposed to have, you can build a K-theory class from suitable families of essentially self-adjoint compact resolvent, which is like saying Fredholm. Hilbert space operators. Maybe I should be a little bit careful here. We have this funny notion of unbounded Hilbert space operators, which are only partially defined. These things, whatever they are in detail, and that's what we discussed last time, define classes. In this group. And if the Hilbert spaces here are infinite dimensional, well, that's where Kasparov's theory achieves its full power. But if the Hilbert spaces are infinite dimensional, you're quite a bit away from what Thier and Hirsebruck originally taught us about. If X is a compact space, the way you define this abelian group K of X is you look at all vector bundles over the compact space. You build the so-called Grothendieck group of all isomorphism classes of vector bundles, and that's what K of X is. And infinite dimensional things involving families of unbounded operators on infinite dimensional spaces, that's a little bit far from what Thier and Hirsebruck were thinking about. But there's an interesting intermediate collection of examples which are in the world of Kasparov on the one hand, but they're also not far at all from the world of Thier and Hirsebruck on the other hand. And that's what we talked about kind of briefly, what we talked about last time. And I think I made a mistake last time. So one of the things I can do right now is correct that. There is this famous bot element in the K-theory of an even dimensional Euclidean vector space, like at the top here. And for this, we need a collection of essentially self-adjoint operators mapping Hilbert spaces to Hilbert spaces, some family of Hilbert spaces to itself. And those Hilbert spaces should, of course, be parameterized by E. And it's kind of nice how it's done. You just take Clifford multiplication by E as a map on a spinor vector space just for the single vector space E. So S is not a bundle, it's just a single vector space, as we were discussing, on which, for example, every orthonormal basis of the vector space E gives rise to a family, or finite family of Clifford matrices, as we discussed at the very beginning of the last lecture. And I left a little bit of space here because according to our axioms, C of E is skew adjoint, whereas according to Kasparov, well, Kasparov wants to consider self-adjoint elements. I mean, there's not a big difference between skew adjoint and self-adjoint. You can always multiply by the square root of -1. It's a little better to multiply by the grading operator like this. So gamma is the operator on S, which is equal to 1 on the positively graded part of S and -1 on the negatively graded part. And when you look at this fellow, where there's a multiplication, some multiplication by -1 somewhere, this converts C of E into a self-adjoint operator, which is kind of nice. And that's it. So here's a family of, well, essentially self-adjoint compact resolvent operators. Are they unbounded? Well, not really, because this S is a finite dimensional Hilbert space, and C of E is just a matrix. It's not densely defined. Any dense subspace of a finite dimensional space, of course, has to be the whole space. But somehow, by default, I mean, unbounded is supposed to mean not necessarily bounded. In that sense, C of E is an unbounded, or gamma times C of E is an unbounded, essentially self-adjoint operator. This family is unbounded in a second sense, which is that as E, the vector E, little e, inside of big E, as it wanders off to infinity, the norm of this operator, gamma times C of E, the norm goes to infinity. So the family is unbounded, even if it's pointwise bounded. And that means that Kasparov is doing a little bit of something or other for us when he builds this, when he describes this construction. Yes?
Right. So when you talk about conjective point operators, the domain goes to subspace.
Yes. So
That's
yeah, but I mean, these are linear operators.
yeah,
So,
no, I was
yeah.
curious because you said any dense subspace has a finite dimensional space, that's everything.
Yes.
That
Which is
actually a subspace.
oh, it's actually subspace. Yes, yeah, dense. These things should be defined on subspaces. Otherwise, it's hard to express what it means for the operator to be a linear operator. God forbid that we should consider non-linear operators. Oh my heavens. Anyway, so this is an example. And the point about this example, the reason I'm harping on about it is that it's sort of halfway between what, the full potential of Kasparov's theory, which allows you to deal with infinite dimensional fibers, Hilbert spaces S, here S is finite dimensional. It's in between that and what Atiyah and Husserlbrook invented. And it's no big deal to take this element, which is written in Kasparov speak, and convert it into something which is written in Atiyah Husserlbrook speak. So the topologists know exactly how to handle these elements, and they know how to calculate these using their Chern characters and so on. This is perfectly within the realm of easy management by the algebraic topologists. In fact, when Atiyah and Husserlbrook invented K-theory, they invented it almost exactly to find a place to put these elements. That was before there was K-theory, there was this type of thing. And so this somehow predates K-theory. It's the reason that K-theory exists, to find a place to put a construction like this. All right, and then there was a slight variation on this. Small generalization. So this guy here, we gave a name to. Let me give a name to it here as well. I think we called it beta of E S. It doesn't, I mean, there aren't many choices for S if E is just a single vector space. Up to isomorphism, there are two, and they only differ by the Z mod 2 gradings. Here it's a little more complicated. If you have a vector bundle, how did I do this? A compact space like we have here, and a real Euclidean vector bundle over it, you can ask for a bundle over M, which is equipped with one of these Clifford multiplications that we were talking about. And if that's the case, you can build this sort of thing again, gamma of C of E. Maybe I'll call it V for vector. Should be a map from S of pi of V. S of, I mean, the fiber at pi of V, maybe I should call it something like this. SV at pi of VM. What did I call it? Just S of V. So this is a family, again, of operators. They're all essentially self-adjoint, if I remember to put in the gamma, which I did. They're all essentially self-adjoint. There are gradings on the fibers, which there have to be. This compact resolvent condition is satisfied. All of the technicalities are satisfied. And this gives another example. And this is so similar to the first one that it's also true for this, that this is well within the realm of the Atiyah-Husserlbrook theories. Easy for the topologists. Even before there was K-theory, it was easy for the topologists to understand what was going on here. Actually, there was a small gap. The first paper that Atiyah and Husserlbrook wrote, they had a conjecture about this element, but by the second paper, they'd figured it out. All right.
Is this picture where you're looking at operators from that desk? I know that Nigel has a picture of the period, like complexes with the cyclic at infinity. Is that?
Yeah, that's exactly what's going on here. like these are complexes of length 2, or
Yeah, yeah, yeah.
indexed, if you like, by Z mod 2 instead of by Z.
Yeah.
Finitely supported complexes, obviously, indexed by Z mod 2.
Directly wants to go. Yeah, it's a go to how we have that. You ever have a difference of vector bundle?
Ah, that's a good point. Maybe that's worth talking about. Let me put a little asterisk here. If you have a couple of, what shall I call these guys? I'm running out of good letters. V stands for a real vector bundle here, and S stands for a spinor bundle. I don't know. T1 minus T2. H. Suppose you have a couple of complex vector bundles. Each complex vector bundle determines a class in the K theory of X, according to Atiyah and Hesselbrook. Maybe H stands for Hesselbrook. And you can get this class from the Kasparov point of view just by looking at the family of zero operators, from the fibers of H1 to the fibers of H2. Zero is not much of an operator. Oh, hang on, that's not quite right, because we want this self-adjoint thing. So let me fix that somewhere. Zero and one and two. Like that.
Sir, I had just one other question. When you say the equivalence class H2, so it means that all operators HI such that this, I mean, when subtract, what is the equivalence class? I mean, how is
Up
the
here,
equivalence class?
are you asking about this top line that I'm pointing to?
No, the line, second line.
This one.
No, the line above. You mentioned about an equivalence class. I just wanted to know how the equivalence class comes in.
I'm not sure exactly what you're referring to, but these families that Kasparov builds, discussed over here on this board, what Kasparov says is that K theory is homotopy classes of families of the type that I'm discussing.
Okay.
So the equivalence relation is homotopy. And a
Okay.
homotopy between two cycles over X is a cycle over X times the closed unit interval.
Thank you.
We'll see some
Thank you.
homotopies today. All right, good. So it's very easy to go in one direction, not so easy to go in the other direction. And it's there are extra problems when X is not compact. But if X is compact, the relationship between, in one direction, between the Atiyah-Hesselbrook theory and Kasparov's theory is very easy. All right, good. And one more thing. In the index formula, maybe I'll write it like this. So one of the things that Atiyah and Singer already knew when they started out to prove the index theorem is they already knew what the answer was, at least for these Dirac operators. And of course, they had a lot of examples, and they knew a lot of algebraic geometry. So they knew what the index of the Dirac operator was going to be. And they knew for sure that a construction related to this Thom element and related somehow to the way that you fit the normal bundle of the manifold into EM for example, using some tubular neighborhood construction, they knew that this was going to be relevant. And we have a nice way of understanding what that dotted arrow means, which is going to play a role here. Suppose you take the K-theory of the deformation space associated with the embedding of M in E, the deformation to the normal cone. Let's not consider the whole thing. This manifold is equipped with a submersion down to the real line, and let's just consider the bit between 0 and 1. Like that. K-theory is a contravariant functor for reasonable maps of locally compact spaces. And so you can restrict to t is equal to 0, and you can restrict to t is equal to 1. When t is equal to 1, this deformation to the normal cone, this family of smooth manifolds parameterized by the real line, the fiber is just E, but t is equal to 0 is special, and the fiber there is the normal bundle. And by virtue of what we were saying when we were listing the properties of K-theory, this restriction is an isomorphism, because if you take the 0 fiber and you subtract it out of this big space that we have at the top of the picture, what's left is a locally compact space which is contractible in the sense of locally compact spaces. It means that the one-point compactification is contractible to a point through maps which preserve the base point. And so that means that there is the associated restriction map. This is restriction at 1, if you like, and here's restriction at 0. The restriction at 0 map is an isomorphism. The restriction at 1 need not be. But anyway, from this diagram, there's now a unique map that you can put here. And that's what Atiyah and Singer knew was relevant, this particular map. They didn't build it using deformations to the normal cones, but they built it using tubular neighborhood embeddings. But the deformation to the normal cone is a little bit better in a way, because it's completely canonical. You don't have to do, if you have the normal bundle, it's some big thing which is straight in the fiber directions. The fibers are vector spaces. And to take that normal bundle and fit it as an open subset of E, you have to sort of push down the fibers. You have to deform the normal bundle to make it squashed somehow, like a disk bundle, and then you can sort of attempt to embed it in. So it's much more natural to do this, and we'll take advantage of that in a moment. Yeah. This space, the part of the normal bundle which lives between 0 and 1, after you remove the part which is exactly over 0. So a half open interval, yeah. No, it has nothing to do with the geometry of E. No. Any half open interval times a locally compact space is contractible in the sense I was just talking about. So even if E was any manifold, you could still do this construction here. All right. And we were calling this something like iota star. It's an example of this so-called wrong way functoriality of K-theory. There's an inclusion map, let's say. There wants to be an inclusion map from the normal bundle into E, but given by some tubular neighborhood embedding. And K-theory is supposed to be contravariantly functorial. So there wants to be a map from K of E back to K of N M, but we're not interested in that map, which doesn't actually exist, just wants to exist. But the other map, this wrong way map is what we're interested in. No, these are all topological spaces. Instead of writing this, in this lecture, I'm K of 0 of X, I'm just C0 of X, I'm just going to write K theory of X. In homage to Atiyah and Herzberg, where are they? Here. Because it's all about, we're trying to push this entire index problem into the realm of the algebraic topologists. We're going to get it so far into the realm of the algebraic topologists that we can just say to them, well, over to you now. Our work is done, like Superman, and we can zoom off, fly off into the sky, and the topologists can, on the ground, scurry around like pigeons with lots of crumbs and figure out what the index theorem actually says. Yeah.
And
Sorry.
I'm still kind of torn out, but I think I figured out. Okay, so you look at open 0, close 1 times E, 1 point to clarify, you get a column,
Yes.
and so you just slide down the column. Okay. That's all.
Just to. So if here is E, and maybe E is a circle,
Yeah.
then the space you'd get here would look like that. So the part of the DNC, in short, to repeat, that you have when you remove the special fiber, it looks, maybe it's hard to think about it as a locally compact space, but when you one-point compactify, which is built into the Thier-Hurstbrook theory, because it's a theory with compact supports, you get a very simple picture. Okay. Yes. Oh, yeah, you had a question.
You work on screen for it, the root instead of just the 0 containing the results, and then you reconfirm to identify the 0 result. You do the same thing again.
Yeah, so I'd sketched this argument of Alain Connes using the tangent groupoid. And what we observed in that argument is that although Alain is trying and successfully trying, he succeeds in converting the index problem to some problem more or less formulated in the language that topologists can deal with. The conversion process is much more complicated. And so the conversion process needs further thought. The conversion process, as you say, involves some sort of harmonic analysis, some Fourier transform. It's a little bit complicated. And what I'm trying to do is get to the essence of matters from at least from the point of view of the geometric people. Okay, so I'm trying to resist saying in this lecture C-star algebra, and certainly resist saying groupoid. What else should I resist saying? Not Hilbert space. We have Hilbert spaces. Okay. Not that there's anything wrong with C-star algebras.
Reality.
Yeah.
More like homology with compact support.
It is?
But then the wrong way to reality would be the right way to reality.
Yes. Yeah, indeed, there is a map from the one-point compactification of this space to the one-point compactification of this space. That's true. So in that case, you're absolutely right. This is an instance where wrong way and right way functoriality happen to agree because you're in the codimension 0 situation. Yeah. Yeah, if you have a map from X to Y, which is proper, which means that it extends to a map from the one-point compactification of X to the one-point compactification of Y, then what you get is a map of a pullback construction on Kasparov cycles, which takes cycles for Y back to cycles for X. So it goes in the wrong way. But in this codimension 0 situation where you're embedding NM, potentially, if you want to use tubular neighborhoods as an open subset of E, it just happens that wrong and right way functoriality agree. Just to add to the confusion. Okay, good. And what we're supposed to prove. So although we have, what I'm trying to say is that although there is this Kasparov stuff in the background, none of the Kasparov stuff really in a serious way intrudes at least into the statement of this theorem. This statement, in other words, is intelligible to many more people than Kasparov. That's the claim. So it is, in that sense, an answer to the question, what is the index of D? Which is an integer, and I'm speaking of this index down here, the second one, which is on the board. And it's a famous theorem of Bott, that the Bott element generates the K-theory of E. This is a free abelian group, with one generator, namely this thing. what I've written down here is an element of the K theory of E. It's just, you know, index some integer times the generator. And if you know what this element is, of course, you know what the index is in principle. And we do know what this thing is. It's just this construction that we were just talking about, evaluated on beta of M, normal bundle, and then some spinor bundle for the normal bundle. And I'm not quite finished. So this is an identity, first of all, in the K theory of E. It makes sense. We have here apple equals apple, where two things are equal, which at least live in the same abelian group. I was emphasizing that these spinor bundles are not unique. So you need to answer the question, which S of M are you talking about here? And that's answered by a little bit of additional hypotheses. If you take the trivial bundle over M with fiber S, this is a spinor bundle for the trivial bundle over M with fiber E. And if this thing is STM tensor hat, so now I'm recalling some technical stuff that we were talking about last time, tensor ST, and not quite. The math tells you should put a bar over this. The bar of a vector bundle is, complex vector bundle is the very same vector bundle, except you change complex multiplication. So lambda times a vector in the new sense, like I said last time, is lambda bar times the vector in the old sense. So this is as spinor bundles for the trivial bundle E times M, which is the direct sum of T of M and the normal bundle. Then that's the formula. So what's on the board, apart from index of D, everything is completely finite dimensional and geometric and intelligible by people who study the works of Atiyah and Husserl. That's supposed to be the point. And now what Kasparov does is, well, once you've absorbed the Kasparov theory and this funny little diagram here, it's obvious how you're supposed to prove. This guy. So that's Kasparov's contribution. It's self-evident what you're supposed to do, namely, construct some class, like I said, in this big K-theory group that we were writing down. That's right. So that when we apply this restriction to 0 to it, ending up here, we'll get the Tom class, M, N, M, S, N, M. And on the other hand, when we apply res 1, we'll get the bot generator times the index. Because if you can find this alpha, and if it does have these properties, then by definition of iota star of this Tom element is the bot element times the index, and you're done. So you just have to make a particular construction. And what should the construction be? Well, it's supposed to be an element in the K theory of this deformation space, at least the part of the deformation space over 0, 1. So of course, what we're going to do is build some family of essentially self-adjoint operators parameterized by the points in this deformation space, and then we'll be done. If we can calculate what the restrictions are. And there aren't many alternatives, really. So let's just see how it goes. Good old Kasparov. And so I was beginning to tell you about the construction last time. Decided to fiddle with the signs a bit to make, well, possibly just to make the presentation correct, but also to make it more consistent with what we did a little bit earlier. So I have a couple of formulas here which I worked out. They're very easy formulas. They're easy to check once you've written them down, but you have to think to write down the right formula. Anyway, so I want to build a family of operators like in the far, whatever it is, left, no, right? Anyway, over there on that board, on as far away from me as you can get almost. I want to build a family in the sense of Kasparov of self-adjoint, essentially self-adjoint operators, parameterized by the points of the deformation to the normal cone. And the way I'm going to do it is I'm going to build a submersion to the deformation to the normal cone. And the fibers will be certain manifolds if this is a submersion, and then I can take the L2 spaces of the manifolds. Maybe I can throw in some vector bundles, spinners, and so on. And that's what the family of Hilbert spaces is going to be. And then we just need to build the operators. And to make math work out nicely, in my opinion, you should do it like this. This submersion is going to be a map of manifolds over the real line, if you like. So it's going to commute with the obvious projections down to R. So in the final coordinate, certainly want to put a T. And what I want to put in the intermediate coordinate is M minus TE. The reason I want to do that is that such a map, as I've written down, automatically has a continuation to T is equal to 0, which looks like this. What I'll do is just take, checking my notation, proj M of E. So proj M is just the projection from E to the tangent bond space at M of M. Oh, I missed a minus sign, but I'll put it in.
So M can be used to carry that over M. That makes down. M can be that R.
Yeah.
So does the map come from reality?
Yeah, it's that map, but we're going to have to do a calculation. We're going to construct a bunch of operators, and so it's much easier to know what they are. Yeah, sorry, and what. Yeah, I mean, that's comforting to know that there is this way of thinking about it, which makes it seem familiar to certain people. Okay, so what do we know about this deformation to the normal cone? We know what the interesting smooth functions are on this space. There's a bunch of functions on this space which are smooth and they're not very interesting. For example, the projection function from this space down to the real line is smooth. The interesting smooth functions look like this. You take a function on E, which vanishes on M, and then to build a smooth function on this space, if you have a function H on E, which vanishes on M, you can look at this thing, H of M over, excuse me, H of E over T. So that's a function on the generic part of the deformation to the normal cone. The part away from the fiber T is equal to 0. And it's a fact, it's by construction, by definition of the deformation to the normal cone, that this smooth function defined where T is not 0 extends to a smooth function when T is 0, in a neighborhood of T is 0. That's what the deformation to the normal cone is all about. And what is the extension? Well, the extension is you just a point in the fiber at T is equal to 0 is some normal vector, and you just apply the normal vector to H. That's what the extension is. So if this map is to be a smooth map, it should have the property that when I compose with one of these special functions like I was just describing, the composition should be smooth. And the composition is just going to be a function on m times e times r, so we can easily check to see if it's smooth or not. What is the composition going to be? It's going to look like this. M, E, T goes to H of M minus T, E over T. And for sure, this thing extends smoothly when T is equal to 0. And when T is equal to 0, what you get is minus the derivative exactly as you want. Minus because of this minus. So I'm just indicating how you know that this is a nice smooth map. Yes, I didn't write it, but this is all correct if H vanishes on M. If H is a smooth function on E and it vanishes on M, then the thing in the top right-hand corner, which is defined when T is not equal to 0, extends to a smooth function. And so whatever I write down for the formula for this map, away from T is equal to 0, I want to check that it does extend to a smooth function, and it does by the criterion. It does at least after you compose with these functions H. All right, good. So this is the map we're going to study, and what are the fibers? Let me call them M sub ET, like that. This is why I've got the notes. Just get the signs right. Yeah. The fiber over a normal vector, ym. And when I say normal vector, I mean a vector which is perpendicular to the tangent space here. This you can easily calculate. This is just m xm minus ym, just because the minus sign's 0. So it's all really concrete. So we're taking M and we're taking advantage of the embedding to sort of stretch M, as you've seen. And in the limit of the stretching, what you get is a copy of the tangent space of M. Kind of nice. And yeah, where it is my eraser? So we have a submotion. We have a family of manifolds parameterized by the points of the deformation to the normal cone. And in order to do Kasparov theory, I want to put an operator on each manifold. And then I'm going to take the Kasparov element, the index element of that family, and that'll be my alpha, the one I'm talking about up here. So I'm going to build an operator. Oh, first of all, I need a vector bundle. Here's the spinner bundle on whose sections our Dirac operator acts. And let's just pull it back to M times E times R in the obvious way via the projection just to M. Now I want to build a bunch of operators on the fibers of our submersion. So what's going on here is that W is a point in our deformation space. And what's bundle-wise, what's going on is I'm taking the bundle STM, I'm pulling it back to this space, and then I'm just restricting it to a fiber. But I'm not going to write pi star of STM restricted to the fiber. It's too messy, so I'm just calling it STM. Okay, and what are these operators going to be? Well, there are two types of points in the deformation to the normal cone. There are the generic points, and then there are the special ones. And for the generic ones, I'm just going to take t, extract the t coordinate, and use that to multiply against the Dirac operator. What about the Dirac operator? The Dirac operator acts on M. But what I'm doing is I'm identifying M with this fiber in the obvious way. What is the obvious way to identify this fiber MET with M? Well, just projection onto the first coordinate. Under that projection, under that diffeomorphism, the bundle I've just built is obviously going to be just the original bundle STM that we started with. So it makes sense to say that on this fiber, the operator is going to be D. Nothing complicated going on here. And as for the special fibers over normal vectors, I'll just define those to be the symbol operators that we've seen again and again and again. The operators you get by choosing a local coordinate system, if you like, writing down the operator in local coordinates, freezing the coefficients at the point M, and dropping the lower order terms. And that makes sense too, because if you take this bundle STM and you restrict it to the fibers at t is equal to 0, here they are, then because we're pulling back the vector bundle STM over there by the projection onto M, you actually get a constant bundle over these 0 fibers. At t equal to 0, the bundle you get on which this operator, on whose sections of which this operator is acting, the bundle is the constant bundle whose fiber is the fiber of STM over the point little m. So it's all really simple there. It's all constant coefficients. At t is equal to 0, we're getting constant coefficient operators, which makes sense because the bundle on which these operators are acting are constant bundles. So easy, easy, easy. Yeah.
Normal equation for P to N into M.
Sorry, can you?
Like P goes from M times D times R.
The deformation to the normal cone.
But of P to M.
Oh, I see. Sorry, there is a typo. Thank you very much. M. Yeah.
Those projections from P to the tangent.
This projection, this is still correct. It's the orthogonal linear projection from the vector space E to this tangent space. Yeah, I'm thinking of these tangent spaces geometrically, like, when you draw a sphere in R3, you can see the tangent space. I'm thinking of that tangent space. All right, that was that, yeah. We're not quite done. This is not the family of operators that we want, but it's really close to the family of operators that we want. I need to fiddle with these operators a little bit, and I'm going to fiddle with them by using, maybe I should call it CW2, same thing. Let me put a C here, if you don't mind. Most of these fibers are compact, but not all fibers are compact. But let's just always have our operators acting on compactly supported functions. Here is the S, which is the spinor vector space for E in the formulation of the index theorem up there. So I'm speaking here of honest to goodness vector valued functions. There is no bundle, except for the trivial bundle maybe, in this line. And this operator is going to be a super easy operator. If I have a function, I guess I'll call it S anyway. And I want to evaluate it at the point of W. Maybe the point of W is some M, E, T, of course, the point of MW, I mean. All points of MW have the form MET because they lie inside the threefold product. And all I'm going to do is I'm just going to multiply by the Clifford multiplication by the E variable like this. Sorry, there we go. It's a multiplication operator. It's a matrix valued function on MW, and I'm multiplying by a matrix valued function. It's a slightly complicated matrix valued function. If you restrict to one of these special tangent space fibers that we see here, it's a linear function. It's a linear matrix valued function. If you restrict to one of these fibers here, it's a complicated function, which is a function of M because of this M that appears in this slot. It's Clifford multiplication by 1 over T times M minus E. So it's a complicated thing. So sue me that, it's just what it is. Okay. What is? This is the grading operator for this, in this case, the spinor vector space S. And what we really want to study is the operator we just defined up there, plus the multiplication operator we just defined below. And now this acts on the tensor product of ST of M with, well, in the sense, tensor product of vector bundles with just the constant bundle over MW with fiber S, like that. That's it. These are the operators that we want to examine. So yeah, that's what we want to examine. And to get a sense, so it's a fact that these operators constitute a cycle for Kasparov's theory. And I'm not going to prove that. That's a matter of functional analysis. The essentially self-adjoint condition isn't particularly obvious for any of these. Why are Dirac operators essentially self-adjoint? Well, that's a theorem in analysis. What about when T is equal to 0? Now we're talking about non-compact manifolds. Is it still true that the operators are essentially self-adjoint? Well, yeah, it is true, even if you add this funny potential term, this one. But in order to make you feel better about this family, let's just try to calculate what's going on. And the most interesting case is when T is equal to 0. So for those operators, therefore, which lie over points in the deformation to the normal cone, which are actual normal vectors like this. Okay. So what does this operator look like? The fiber on which it's acting is a vector space. We identify that fiber, somewhere it's over here, with a vector space. By projection onto this coordinate here, it just becomes the vector space T of M. So we're talking about operators on T of M. And the question is, what is this operator? Well, it has a part coming from DW and a part coming from CW. And the part coming from DW is as we discussed, what you get by taking the Dirac operator and freezing coefficients. Yeah, that's it. And dropping lower order terms. Yeah, I knew there was something else. So it's going to look like this. So what I'm looking at here is the following. I'm choosing an orthonormal basis inside the tangent space. Once I've chosen an orthonormal basis, there's a corresponding system of coordinate functions, and I'm differentiating with respect to them. And this is the Dirac operator after you freeze coefficients and drop lower order terms. Tensor with 1. And that's this part, but now there's this part to consider. And what's that? Well, if we're at some point in the tangent space, some x, of course, we can write x as a linear combination of the basis vectors, and that's exactly what I'm going to do. What I'm going to get here, which is the right way of doing it, is this. But we're not quite done, because there's this final y here that we have to take into account, and we'll also get sort of the same sort of thing, 1 tensor gamma Clifford multiplication by y. This one. Now we're done. We want to understand what's going on. This is the operator. We're trying to understand this operator. I'm trying to make you feel happier about this operator. And the first thing I'm going to tell you is that the first 2 terms, well, anti-commute, as they say, graded commute with the third. So let's just consider the package consisting of the first 2 terms and then trust that we can handle this little thing later. Okay. That's supposed to be a little x. And it's a scalar function, a coordinate function on the vector space TMM. If you choose an orthonormal basis, there's a corresponding system of global coordinates on the vector space. CJ is a typo. C. Yeah. Sorry. My apologies. Got a little too excited. Well, here's a function. Here is a function. Okay. The function is Clifford multiplication by E. If E happens to be a linear combination of some vectors xj and maybe a yj thrown in, then Clifford multiplication by that linear combination is a linear combination of Clifford multiplications, because little c is a linear map, and that's all I'm doing.
I see. The coordinate.
Yeah. What are we doing? I guess we're doing fine. So now let's use the following fact, which we haven't used yet, but it appeared in the, oh, it's still up there. in the definition of in the formulation of the index theorem, which is the way in which these various spinor bundles are related to one another. We have to use that, of course, because there are many different spinor bundles, and if you change the spinor bundle, you're likely to get a different answer. So we have to use this particular fact that you see up there. And I'm throwing in this complex conjugate. You'll see where it comes from in a moment. It's a very modest role that it has to play, but it does play a role. And we're going to use this. Say again? Yeah. Thank you very much. That was my, for what it's worth, notation.
Well, on this side.
Oh yeah, anything else?
The project, so is this actually right? Is it projection to the tangent space? Because I thought it should go into like the normal bundle or something.
Excellent work, Jacob. Extra gold star for you. Yes, thank you. Let's call that a typo. Good. So let's consider our operator, which I'm now trying to copy down better than I was writing things down before. So I'm just trying to transfer what you see up there. I think I need that. Oh, I see. There should be a. So here's the first two terms of the operator, which I tried to write down correctly. I think I maybe did. Against all odds and all your expectations. There it is. Okay, on. It's acting on this vector space, but what exactly is it acting on? Well, we have to pull back this bundle STMs like we were discussing up there to the tangent space. There it becomes the constant bundle with fiber S. I'm not quite sure how to do it. Where to put the little m like that. What about these Clifford multiplications here? Well, the x's all act in the tangent direction. They all are tangent vectors. So the Clifford operators are actually acting on this factor and not on this factor. They're acting as Clifford multiplication here, tensor 1. So this whole operator that you see up there, not the whole operator, but the first two terms, is acting just on the first two factors of S of Tm, tensor S of Tm bar, tensor S of Nm. Another way of saying that, which may be or may not be better, is to say that the operator which lives up there, the first two terms of the operator which live up there, correspond to this operator on this space, tensored with the identity on the vector space S and sublittle m, m. So it's really this operator that we're trying to understand. So and when you play around in index theory with Dirac operators long enough, you know that the right thing to do as soon as you have a Dirac operator, because kind of it's how Dirac defined it, is to square this thing. Do you have a name for this? This thing squared, I'm not going to write it all out again. So what happens is kind of interesting. It's the sum of a bunch of terms. If you just look at the first part, it's like Dirac's operator. Here are a bunch of Clifford matrices which anti-commute with one another. So when you square just the first term, all of the cross terms go away. And what you'll get, because each of the Clifford matrices squares to the minus the identity, is you'll just get minus the Laplacian. That's easy. All of these Clifford matrices, because of the gamma, square to plus the identity. So we'll get this fellow here. And then there are going to be cross terms, which arise when you multiply something in here against something in here, plus, and then you do it the other way. You multiply thing against thing in the other direction. And what are those cross terms going to be? Well, they're going to involve, because the coefficient matrices anti-commute, it's going to involve the commutator of ddxj with xi, but that commutator is delta ij. And what's going to come out of this is just c of xj tensor hat gamma of c of xj. And the only little nuance to keep in mind is that the second c of xj is not exactly the same as the first. It's acting on the complex conjugate vector space right here. So that's the precise explicit formula for the square of this operator. And so now reasonably minded people will ask the question, what is this? Let's just call it H, so I don't have to keep writing it down more than one more time. Here we go. Yeah. Well, let's look at an example. It mentions two. It's actually a very interesting example. Lots of interesting indexes on surfaces. So there are two xj's. There's an x1 and an x2. And so there are two Clifford matrices in play here. And they're unique up to unitary equivalence. So we might as well assume that one of them is this fellow. As we discussed some time ago, the other one is the other Clifford matrix. These have to be matrices which are skew adjoint, like these two are. Each of them has to square to 1, and they have to anti-commute, like they do. And then there's a grading operator. And the uniqueness theorem, which we began the last lecture with, disregarded the grading. So there are actually two copies, two possibilities for the grading, which differ by a sign. Up to unitary equivalence, this is the complete story. And now you can calculate what this guy is. I mean, just for fun, just like Isaac Newton did, you can just calculate, but much easier, you can just calculate up to unitary equivalence. This matrix looks like this. The eigenvalues are 2, 0, and -2, and the 0 eigenvalue is multiplicity 2. We'll look at this in another way in a moment. But you got to just do it, right? You have to multiply the 2 by 2 matrices to feel good. And an interesting thing happens when you do this, which is that the 2 eigenvector is really, really special. Sorry, the -2 eigenvector. Now I'm worrying that I made yet another typo, but I'm just going to let me just point out that if when we defined this operator, we put the gamma on the other side, that would change everything by a sign. And I'm a little, I cannot think with my head fast enough to know whether the signs I'm about to show you are right or they're wrong. So what I'm about to say may be off by a sign. And if that's the case, I have to go back in the notes and move all the gammas to the other side. But let's assume I got it right. here's what the two eigenvectors look like, or they look like this. This, or I should say, this particular guy is a two eigenvector. And the interesting thing is that this works for any orthonormal basis of S. S being SM, STMM, I guess we called it. There's something canonical about the, and coordinate free about the -2 eigenvector, which is not true about the other eigenvectors, or not completely true about the other eigenvectors. And what I've written down is either true, or what I wrote down was a true statement about the 2 eigenvector. I really want it to be a true statement about the -2 eigenvector. I'm not that for sure. But to be honest, I'm having doubts, which I will resolve in the notes. This is the story when n is equal to 2. Maybe I should just continue, running out of time. But this operator is well known to the physicists, and it's well known that this guy here is always bigger than or equal to n, 2k. This is the famous quantum harmonic oscillator, or it's a sum of 2k many quantum harmonic oscillators, one on each coordinate line in this 2k dimensional space. And these operators, yeah, what I mean is, if you call the operator for a moment Q, what I mean is that Q VB, we'll call it SS. In the sense of operator theory. 2k in this particular case, yeah. Thank you. If an operator is bounded below and it's self-adjoint, then actually self-adjoint, then it's invertible in the sense of unbounded operator theory, and that's exactly what's going on here. The operator is invertible, and the only way you can restore some interesting index theory to the situation is by bringing down the spectrum of this operator from 2k to 0, which means you have to look at the -2k eigenspace of this operator, which exists. It's not zero-dimensional, it's precisely one-dimensional, and that's the dimension. We did a calculation when k is equal to 1 here. There's a very similar calculation you can do for any k. It's always the case that the spectrum consists of even integers between k and -k going down by 2, k minus 2, k minus 4, and so on. That's always the case. And because secretly there's some, anyway, that's always the case. And the -2k eigenvector always has this form, except you don't stop the sum over up to 2, you sum all the way up to 2k. And this thing is canonical, it's coordinate independent because of the bar here. If you form, for any orthonormal basis, the sum of Vj tends to Vj bar in S tends to S bar, that's a unique canonical thing. It's independent, the sum is independent of the basis, so it's some, yeah, independent of the basis. All right, so I have a good picture now of what the operators are when t is equal to 0. What are these operators when t is equal to 0? Well, if we, maybe I should go on a little bit. If we go back to our operator here, this one, which I'm not going to write down, I'll just continue by writing it like that. And you can put a square in what I'm about to write down, or you don't even need to put in the square. You can say exactly what the kernel of this operator is. It's just the function e to the minus x squared over 2 times this canonical vector here. I don't know, vacuum vector. Maybe I should call it S vacuum. I don't really know why it's called vacuum. Physicists, tidy people, I don't know. The Hilbert spaces on which these operators act break up into 2 pieces. The piece which is one-dimensional, which is spanned by this Gaussian function, and the other piece which is the orthogonal complement to this piece. And on the piece where we have, oh, I didn't finish this statement, this is 0. And on the piece spanned by the Gaussian vector, the operator is 0. Whereas on the other piece, the operator is bounded below by 1, or not 1, but 2k, in fact. Okay. Because the eigenvalues are all, like I said. So they're invertible. If you look at the operators at t is equal to 0, they act on a family of Hilbert spaces, and this family of Hilbert spaces breaks up, which is parameterized by M, and it breaks up into a trivial one-dimensional bundle, which is the one-dimensional bundle spanned by these guys. And it's trivial because this is a canonical vector. It doesn't depend on any choice of basis or anything. So the field of Hilbert spaces over which our family of operators acts when t is equal to 0 is always the direct sum of a trivial field. I'm talking just about the operator on this amount of this to begin with. That trivial field direct sum an invertible operator, and for the purposes of index theory, you can forget about the invertible operator. Invertible operators have 0 index. When you take t is equal, and now let's go back and throw in the final term of the operator, which we conveniently forgot about up to now. Restoring that piece into the story, here's what we find when we restrict to t is equal to 0. So when t is equal to 0, we have a family of operators parameterized by the points in the normal bundle. That family of operators, now that we've restored this extra tensor factor, that family of operators acts on a certain family of Hilbert spaces. And what is that family of Hilbert spaces? Well, it breaks up into a direct sum of 2 other families of Hilbert spaces, one corresponding to the kernel of the harmonic oscillator, or the shifted harmonic oscillator, and one being the orthogonal complement. The orthogonal complementary part is just 0. This operator is bounded below. You don't even have to worry about it. On the place where the operator is 0, the formula for this guy, this Kasparov operator, is much easier. On the place where this fellow and this fellow act as 0, the operator, of course, is just this thing. But this is the Tom element. So what I'm saying somewhere here. So we have the family that we're really interested in, which are these operators up here. And I'm only interested in those W's which are now in the part of the deformation to the normal cone over T is equal to 0. So this is a family indexed by vectors in the normal bundle. And we have a direct sum of an invertible family. Actually bounded below uniformly by 2. Well, the square is bounded uniformly below by 2, so the operators are bounded by the square root of 2. And the family which defines the bot class. We built a crazy family inspired by Kasparov, also inspired by what we know about the harmonic oscillator. We built a crazy family. We try to study this family. What we find about this family is that when you restrict to t is equal to 0, it has an extremely simple form. And as far as K-theory is concerned, which doesn't care about invertible families, the index of an invertible family is 0. As far as K-theory is concerned, it's just the Tom element. Did I call it? Didn't call it anything, but this is the Tom element. We built family alpha, and we just discussed that the restriction to 0 of alpha is the Tom class. And it wouldn't quite be the Tom class, at least not necessarily, if you didn't put the bar here. And the reason it wouldn't quite be the Tom class, at least not necessarily, if you didn't put the bar here, is that this family of kernels spanned by these functions here, they'd still be one-dimensional, but they might define a non-trivial line bundle over M. So you'd be off just by a little line bundle. But since we had the foresight to put in the bar, we get this equation here on the nose, rather than this guy here times some line bundle on M. All right, good. And now it just remains to calculate this. This is much easier. I'll do it in the notes, but I'm not going to do it in front of you guys because we're out of time. There were a bunch of technicalities. What I really want you to absorb is just this sentence here. Because we're in this world of where everything is an example of one of Kasparov's constructions, it's sort of obvious how to proceed. And of course, then you have to proceed, and then it gets a little technical. But this is the most important sentence in the lecture.
Thing like a definition space sort of operator on that and sort of
it's yeah, I would say it's I would say this, I mean, this is consistent, perfectly consistent with Kahn's approach that we were talking about a couple of lectures ago. I would say it's not exactly consistent with the original Attir-Singer approach. Their approach is much more brutal. They choose a tubular neighborhood embedding. They do some brutal calculation, which they, you know, they're proving a slightly more general theorem. They weren't just calculating the index of Dirac. So I'd say this, I mean, this could be a model, but it's not a model that you notice or that you observe in nature as you go from one proof of the index theorem to the next.
class operator.
Yeah, that's a very good question. You could hope, for example, that, you know, Eric van Erp speaks about the world's simplest index theorem in the world of Heisenberg, the Heisenberg calculus. Maybe in one or two really special cases like that, you can tweak this argument and make an explicit argument for some classes of, let's say, Heisenberg type operators. I'm not aware of any other examples. Maybe that would be a more honest answer. Not aware of any, but that doesn't mean they don't exist. If you don't use the Dirac, then you'll get something more complicated. right here, and I wouldn't know how to analyze it. That doesn't mean it couldn't be analyzed, but I wouldn't know myself exactly what to do at this stage. Good. On Thursday, we'll talk about something completely different.